Hello folks, my name is Starner. I'm a professor of computing at Georgia Tech. I'm also a staff research scientist at Google and was a tech lead on Google Glass. Today's material is from my classes as a professor, not from Google. And I would like to talk to you today about eye interfaces for IR eyeglasses. My goal for many years now is to enable all-day head-worn displays to augment everyday life. I first started out with this in 1990, writing a grant to the Department of Defense on augmented reality, and to my knowledge, it's the first time that term was actually written down. I had a full system by 1993. You can see it here on the left-hand side, and that was originally designed to take better notes in classes. MIT Media Lab started funding a lot of the work on wearable computers. We created a group of it from 96 to 99 that actually had an annual budget there. And we did a lot of work in HCI, computer vision, augmented reality, AI, affect, fitness, just about everything in wearable computing we touched at one point or the other. And then from 2000 to 2010, I moved to Georgia Tech as a professor. And you note that while we could manage to get a display in the eyeglasses, we could never get a good interface besides a one-hand keyboard called the Twiddler. And that's because on-the-go interfaces are very hard. I should mention that the display that are in the eyeglasses, that's from 1997. That's a time-lapse photograph. The display was made by Mark Spitzer as an experiment when he was running Micro-Optical Corporation. It was a wonderful proof of concept. However, after about a month of using it, I gave up. It was only 320 by 240 resolution. Didn't run my Emacs system very well, and so I really couldn't live my life on that. I switched to a Micro-Optical SV6, which you see here on the right. From 2010 to 2012, I started using Google Glass as my primary machine. December 2010, I was working with the first version of Glass. It involved a laptop and a backpack and a cell phone strapped to my head, the display that was from the military. And this was using off-the-shelf parts just to prove what functionality we wanted. And yes, that cell phone was the only way we could get a touchpad that was multi-touch at the time. Nothing else was available. The system developed rapidly from 2011 to 2012. One of the big observations was we wanted to go lightweight. Originally, Glass was a much heavier weight, bigger system, much more like the Nreal today or even the HoloLens. But the Lennon system in 2011 really pushed things towards lightweight so that people could use it in their daily life. Generally, you want to get systems under 75 grams with a nose rate under 30 grams. Glass was 45 grams. The reason I bring up all this stuff is that there was actually an eye interface on Glass. There still is. It was a proximity sensor that aims at the right eye to detect winks and blinks. By 2012, we were becoming public about Glass, and the founders of Google, Larry and Sergey, would wear these things in public. They were very active in the project, and they were using these things in their daily life. That's Sergey on the New York subway in the upper picture, and Larry at his friend's wedding in the lower picture. We started shipping them to friends in 2013 and had public purchase from 2014 to 2015. From 2015 to 2019, we had the Glass Enterprise Edition that was available for purchase, first for limited partners and then for more public purchase. And last year, we introduced Google Glass Edition 2. That makes Glass one of the oldest head-worn display families out there. Inspired a lot of academic research, including a lot of eye interfaces, which we'll talk about in a little bit. And I believe Glass XC is probably one of the best selling head-worn displays up to its time, if I understand things correctly. So the question is, why are people so interested in head-worn displays? We certainly took a look at it for Glass. That's why we had that wink and blink interface. And Larry was really interested in solving one thing, which was reducing the time from an intention to action. In other words, from the user's idea that they want to do something to their first action to do it, can we get that time as small as possible? And in my research up to that time, it really showed that if you could get the time between intention and action to 2 seconds or under, People will use it all the time, just like a cell phone, sorry, like a wristwatch. People don't think about checking the time, they just do it. They don't even are aware of it sometimes. Once you get your interface slower than 4 seconds, it tends to become a very big barrier for actually using it for more time, or using it in your daily life. And so the hope is that making eye interfaces allows people to refer to the computer quickly for these micro interactions. Another reason to do eye interfaces is subtlety. A lot of folks would really like to be able to check a message without other people being aware of it during a meeting, or if you are deaf or hard of hearing, be able to read captions on a display and be able to control the caption on the display without necessarily calling attention to yourself and your disability. There's also a sense of privacy with the systems. You don't want to necessarily speak out loud in public when using them. Some folks, like folks who do order picking in big warehouses, their hands are full, so being able to control a head-worn display with eyes would be extremely useful. Another benefit is you don't have to have an external controller. You can sell one device, one pair of eyeglasses. This was a big push in glass in the early days. We wanted to sell one device, not have rings or anything else that was necessary to control the system. And finally, a lot of folks get very excited about having a interface you can integrate with physical reality, being able to click on objects, that sort of thing. And we'll get to that in the future of this talk. Of course, probably the biggest point of these head-worn displays and eye interfaces is that Hollywood makes it look cool. And yes, your grad students or software engineers saw this movie when they were 10 years old. So for a lot of them, the thing that formed their memories of what eye interfaces should be was this Iron Man interface. Unfortunately, there's no way you're going to be able to fit that interface in this mask. If you look at the video from Iron Man, he's looking around inside the mask, and that mask is not that big. If you're actually doing an eye interface like that, be more like on the right-hand side here, like an astronaut's helmet. And yeah, you could probably do a pretty good Iron Man interface in the astronaut's helmet, but it's very few people who would wear that around in daily life. With eye interfaces, there are many challenges. One of the biggest is that sunlight tends to swamp the illumination of the camera if you're doing bright pupil or dark pupil, or you're trying to do glint detection. Oftentimes the sunlight will just wash out the glints or add extra glints, or just cause the camera to white out. So that's a difficult problem to deal with, and there's lots of ways you can approach it, but the amount of variability you get when walking or driving or being on the go is quite hard. A bigger problem that people underestimate is fit. Trying to make a camera into a head-worn display so that you always can see the eye is surprisingly difficult. The glasses slide around the face, and you often lose sight of the eye or lose calibration this way. So one of the biggest issues, though, one of the biggest challenges is showing the benefit for the cost. And here I mean the cost of fashion and social weight, how good the glasses work, how good the glasses look, also how they sit on the nose. Do they add too much weight to the nose? Do they reduce the battery life too much or cause the battery to be too bulky? And also the cost. So as soon as you put eye interfaces into a system, there are a huge number of things you got to consider, and it all comes down to, is the interface benefit sufficient? Now, there are a lot of potential benefits out there, and these are some of them that are commonly talked about when people talk about head-worn displays. Let's talk about the first one, which is replacing the mouse, and this is probably the most common one. So a simple question is, why aren't eye interfaces already used for pointing on desktops? And the simple thing is that pointing accuracy is not very good with eye interfaces. Eyes are only under semi-conscious control. They're dancing around all the time. And it's hard to get an intentional and exact movement without having a destination target. Now you can make interfaces with destination targets so that it becomes easier. but you can't just have people look at like a certain angle and expect that to work. The other problem is that eye movements tend to be very jerky. They're saccading, so you're not getting a continuous movement unless you're following a slow target. And finally, you get a lot of user interface problems when you have misalignment of the cursor with where the person is looking. So it feels like you're continually chasing the cursor or leading the cursor, and that leads to a bad user experience. Another problem is that pointing accuracy is surprisingly unreliable as far as the fovea is concerned. Your fovea is 2 degrees, and so on a high-resolution display like what I'm using right now for narrating this talk, that's about 170 pixels. That's a lot of imprecision to not know what the user is looking at. So, if you're trying to do a drawing program or clicking on the edges of a window, it might be very hard to do that sort of fine, precise control. The other problem with misalignment comes with the fovea is the fact that because the fovea is so small, if your misalignment is too big, your user is actually having a hard time seeing what their eyes are pointing at. So that can be another frustrating part of the experience. Finally, is the idea of interface speed. You really have to make a system that can keep up with the eyes. They're very fast. They're the fastest movement in the human body, 700 degrees per second. Saccades are generally 15 to 20 degrees typical and up to 40 degrees in range. They're also very fast. Another thing that limits your interface is that saccades have a refractory period. It takes about 100 to 200 milliseconds before you can saccade again. Now, this can be a benefit. If you are trying to use your eyes to show people, your eyes as a cursor to show people what you're doing, it's very difficult because they have a hard time following it because by definition your saccades are probably moving just ahead of theirs. Just humans, it's very hard to actually see what the person is doing with their eyes. This could also be a benefit. One thing I heard about was an MIT interface where they had a wall of text displayed publicly in Russian, but when the user scanned it, when the user used it, read it, every place they looked was translated from Russian to English, and so the user could read it, but everybody else around them couldn't. And I thought that was a clever use of the speed of eye interfaces. Another standard problem I think you all are aware of is selection dwells are challenging. Even when you're fixated, you still have about a degree of movement, and that's on top of the 2 degrees of imprecision of the fovea. Fixations normally are between 200 and 600 milliseconds. Longer are fatiguing, so if you're going to have people wait for a second to click on something, they're going to get tired of their interface pretty quickly. On the other hand, if you make your interface select based on dwell time too quickly, you get the minus touch effect where they're just getting spurious mouse clicks all over the place. Going the extreme limit on slow, however, if your eyes don't move, and in this case I'm talking about anesthetizing the muscles of the eyes, your vision disappears. Your eyes need movement in order to actually refresh and see the world. So given this problem with using dwells for selection, a lot of interfaces replace dwelling with button presses. Some folks try eye blinks, but they are also semi-conscious control. People tend to try to go with more secure button presses or something for enabling or controlling or clutching the eye movements. So whenever my students propose an eye interface, I always ask them to check out the next closest alternative and tell me why we need eye interfaces versus the other next best choice. And for things like a mouse pointer, a head mouse is a pretty good solution. You just put the cursor in the center of the screen and you pitch or yaw your head to control the X or Y location of the mouse. Now, this is very conscious control, and the body really tries to keep the head stable, so you can even do this somewhat while you're walking if you're not trying to do anything too precise. It's incredibly cheap to do. It's just an IMU, low power, low weight, less fatiguing. And so it really does seem like a pretty good, viable alternative to pure eye tracking. The problem is it's slow. It also has a high social weight. If you're in a meeting, having people see you move your head around is a little bit suspicious. You can do interfaces with head movement with very subtle interfaces, very subtle movement. The problem is as soon as you try to do subtle movement while walking, then you have a signal to noise ratio. So you really have to adjust your gain control to make something that's both subtle and works in a mobile environment. Another alternative to using the eyes as a mouse is for eye gesture commands. Now, this is stuff that was done by Drews and Schmidt in 2007. And they basically just said, okay, we're going to have 8 different locations or directions you can move your eyes. And they correspond to the different corners on a screen. And they just define different gestures for different activities you want to do. And this was very successful. They had pretty good accuracy, pretty good precision, not too many false positives from what I can tell. This is a viable way to go. The only problem is that you really have to have your users memorize what the gestures are. Now, that's sort of against good interface design. Don Norman has a wonderful essay called Gesture Interfaces, A Step Backwards in Usability. I highly recommend it. Whenever my students propose a gesture system, eyes or hand or any sort of gesture system, I always insist that they address Don's objections here. First of all, for these things like these eye gestures, they're not visible. You can't see what's available to you to do, and so the user just has to memorize all the different commands and be able to reproduce them on the fly. It's also hard to get feedback to the user because they're saccading all around already. They don't have the ability to saccade to a feedback location. If they do, there's a good chance that they will mess up their current eye gesture. It's hard to discover new gestures to do, this is something that is only really solved by showing all the gestures all the time. That's not really feasible with a lot of these head-worn displays. Great part of the eye gestures is they're reliable. They are pretty good. You can make the interface consistent throughout the interface if you want, and it's scalable in the sense that it can work on a large screen or a small screen, a desktop screen or a wearable computer screen. The only thing you have to worry about really is your field of view. You are probably not going to be able to do it with a screen that's too big or a screen that's too small, but for most everything that you're going to see in common use, it should work out pretty well. Now, there's another alternative, which is a synchronized gesture interface. Now, this was first done, I believe, by Estevez in a system called Orbits in WIST 2015. And they were using, I think, a Tobii eye tracker on a desktop to control an interface on a wristwatch. We were trying to do something more self-contained. We used something called a Jin's Meme, which is a pair of EOG glasses. It just has 3 electrodes. It's pretty crude in the sense that you're just getting an X and Y, a delta XY signal. But even with that, you can do surprisingly fast and effective interfaces with this synchronized interface. I'll just play the video here so you guys can see a sense of what's going on.
Solar System. Smooth pursuit interactions using EOG glasses. Solar System allows the user to select options without using his hands by recognizing smooth eye movements. We introduce a few application scenarios for the Solar System. First of all, to read the eye movement, we use the Jin's Meme glasses with 3 EOG electrodes. Jin's Meme detects vertical and horizontal eye movement. From the eye movement data of the user following the orbiting dot, we can calculate polar coordinates of the orbiting dot and recognize which orbit the user is following. And for forced choice binary selection, we've already evaluated a 2.6 bits per second input rate at 250 milliseconds per input. Solar System could be useful in cases when the user is unable to use his hands, for example, in a cooking situation, or in situations when it is relatively hard to operate a device using hands, for example, while driving. Solar System can easily interact with any other systems since it is implemented using the TCP/IP socket communication.
So the idea here, of course, is that you have different icons, different prompts, and you have a circling satellite that you track with your eyes, depending on which prompt you want. And you can do multiple selections or multiple things on the screen at the same time. The big problem here, of course, is that you're using up some real estate for those little orbiting cursors, but really it's not that much. And like I said, surprisingly stable system. Now, if we go look back at Don Norman's objections to this, this system is visible because you've got an orbiting cursor, you know what's active. You can give the user feedback because you can, as they get more closer and closer to selecting it, you can change the color of the thing or make it larger. It's discoverable because everything's on the screen that has a cursor, and it's, like I said, surprisingly reliable. And it's scalable. This works on just about any size screen. About any field of view, as long as it's within what humans can perceive. Within a limit. It's probably very hard to do something that's less than a degree or two, but generally for most displays you care about, this will work just fine. Now, when we look at head-worn displays, one of the biggest problems is text entry. And like I said, I use a twiddler, a one-handed keyboard to solve this problem. But it'd be nice if we can make it all self-contained. So a lot of people have looked at text entry using eye tracking, eye interfaces to solve this problem. Now a good goal here is about 40 or 50 words per minute. That's the average speed of a mobile phone expert. It's also a pretty decent desktop speed. If you do a dwell keyboard where you're just dwelling on each letter to select it, you're limiting yourself to 12 to 24 words per minute. However, if you do a shape writing thing where you're going between, you start at the first letter and try to go through all the different letters in the word and end up at the last letter, that's an excellent way to do things with touchscreen typing, but it's a challenge for eye interfaces because the user is often visually searching for the next letter, which causes the path to have spurious wrong moves and possibly inserting characters. When you test these systems, I recently found a student project on this at KTH. They were showing about 7.3 words per minute for word level systems and 9.4 words per minute for phrase level, where you just keep going from word to word to word. One of the coolest keyboards in this space is, I think, by Morimoto. And this is where you're switching between two keyboards. You have the first keyboard at the top, second keyboard at the bottom, and if I was going to type my name, I would search for the T with my eyes till I find it, and then as soon as I find it, I switch to the bottom keyboard and search for the H, then the top keyboard A, bottom keyboard D. And what happens is what we're looking at here is the switch of context to figure out when a letter was selected instead of dwell. So as I'm looking at the T, when I go through the yellow center to H, I then back up the path to see where was the last stopping point before I start on that path through the yellow center, and that will tell me which letter I was on. I think the average words per minute were 12, but you can see here that their best expert was over 20 words per minute, which is pretty astonishingly good. What's cool about this is it alleviates the dwell issue. It allows the user to search visually and not hurt themselves when trying to type. And it also raises the possibility of mapping gestures to words. Because suppose my calibration was off, and instead of doing Thad, I was off to the left a little bit. And so I end up doing RG off-screen S. And there's no word that matches that. And so we can probably figure out that it should be Thad just by looking at a little bit of translation here in the path. So we probably only need relative precision here in, at least for small dictionary situations, probably even large dictionary situations. You can probably get away with relative precision instead of absolute accuracy in where your eyes are pointing. Another system that is EyeWrite. This is a system done by Jake Walbrook. And basically you're going from corner to corner in sort of a unistroke pattern. You get about 5 to 8 words per minute on it. It's relatively gross motions. Again, the problem here is the user has to memorize the letters. I'd be remiss if I didn't talk about Dasher. Dasher is a very interesting interface in that it's predictive. It tries to arrange letters by the probabilities, and you just use relative motion of your eyes to select which letters are coming up. It's intense visual focus, but only relative accuracy is needed here. All you gotta do is move the cursor up and down, left and right. However, the calibration is off. It might be difficult to see the letters to target. Interestingly enough, you can get about 17 words per minute with this, which is quite good for these interfaces. The real question here, though, is the benefit of having this text entry system overcome the detriment to the fashion and the social weight and the physical properties of the device. And so I'm of two minds on this one. I don't think we're there yet. This certainly can be done for heavier weight systems like VR systems, but for AR glasses, we're trying to wear them around everyday use. It's hard. Now let's also talk about eye on screen and focus regions. These are less rigorous versions of absolute accuracy. You can imagine having a system that it only listens to your speech when you're looking at the screen, or only listens to gestures made with your wristwatch when you're looking at the screen. So having the eye on screen as a potential clutch, that might be a good idea, but it is something that you still have to worry about false positives per hour and accuracy. You have a similar thing with focus regions for photography. Folks, some of these DSLRs already, you can look at these different regions and select the focus for that image. Okay. One thing that folks get very excited about, again, is a world-facing camera, coupling that with eye tracking and try to figure out an object of interest. This idea has been around for literally decades. Probably some of the first interesting research done on it was Michael Land, who showed that during a task, when you're in a manipulating task, you're looking at the relevant objects about 82% of the time. Even before the task, you're looking at them about 50% of the time. So the idea is that we can get some idea of the user's context and what they're doing by combining the inner-looking eye-tracking camera and the outer-looking world camera. Now, of course, the alternative here is just simple computer vision. Turns out 95% of the time, the eyes are within plus or minus 15 degrees of center. So if you just do computer vision in that 30-degree cone and look for hands and objects in motion, you can basically predict what the user is looking at already. This is Alireza Fathi's PhD dissertation, where he shows that he can predict the user's gaze pretty well just with this method. And here he's seeing that you're pouring some milk into a cup. You pretty much know what's going on there as far as the attention. Now, some things I'm most bullish about as far as thinking that they are possible and useful are authentication, dawn-off, and physiological signals. Now, physiological signals, just for those who aren't familiar with this, there is a symptom called nystagmus, where your eye vibrates a little bit when you're under the influence. And so when that police officer runs a pen light back and forth in front of your eyes, what they're really looking at is for your eyes to vibrate. And that indicates you're under the influence. So you can imagine having all sorts of physiological stuff where you occasionally prompt the user or ask them to do things and get some physical responses. This might be good for trying to titrate pharmaceuticals, for example. So I really kind of like this space. You can require power rarely to do things. It's often simply a binary decision, and you can gather evidence over many seconds to figure out what's going on. Good trade-off here. I really like the authentication stuff because it's a rare and short interaction when you're first logging into the system. You can have active participation of the user where they're willing to move around and try to get their eye in the right situation for authentication. One thing I didn't mention yet is reading auto-scrolling. This is another eye gesture, and this is a pretty simple thing to do. You just look at the eyes going back and forth and automatically scroll text for the user. So here are my suggested future directions. I really believe in these 4 things right now, at least from what the technology I'm seeing. And if folks are interested, the International Symposium on Wearable Computers is coming up September 12th, where there's a lot more people like me who are intent on wearing computers around daily life and really get a sense of for what these things are most useful. Thank you very much.